Nested loops in JavaScript, and indeed in most programming languages, do not always result in a quadratic time complexity, but it's very common that it does, as is the case with these loops before you. Anytime the inner loop runs a number of times proportional to the outer loop's count, you have quadratic time complexity. However, like everything else in life, you have to have a nuanced perspective. These nested loops actually have a linear runtime because the outer loop will run an nth number of time, but the inner loop is hard-coded to run just 5 times. This, of course, is a trivial example. So I'm going to show you 4 more examples of nested loops having linear time complexity. Here we have a users array, and each element of the array contains a user object with their ID, name, and top lab partners that's inside of a nested array. Now I'm using a JavaScript higher order array function here because I think it's a cleaner pattern, but they're still nested loops. The output that I've highlighted down here will be from the result of the console.log call. The outer for each iterates through each user in the users array. The inner for each loop iterates through the top lab partners array of each user. The top lab partners array has a constant size of 2, as you can see here. So the inner loops operation are constant. The structure maintains the same linear time complexity of O of n as the traditional for loop, where n is the number of users. If you want to use the for loop, this is what the code would look like. Now, I have tested and benchmarked the running time for each, and they're equal. Using the higher order function in this case is equal to the performance of the for loops. Again, both of these example uses nested loops with O of n time. Imagine you have a large data set and need to process it in fixed size chunks to manage memory or send it in batches. This is a common pattern in data processing and networking. The outer loop runs approximately n divided by chunk size times, meaning that the number of iteration of the outer loop is equal to the total number of elements in the array divided by the size of each chunk. The inner loop processes a fixed size chunk of data, therefore it's constant. The total number of operations is approximately n divided by text chunk size times text chunk size, which simplify to n, which is O of n, which is linear. I know I'm spewing out a lot of computer science stuff, for lack of a better term, but think of it this way. The outer loop loops to the data structure, and the inner loop loops to a fixed size chunk, which is constant, right? So this is an efficient algorithm. If you forget all the computer science terminology, just remember that the inner loop loops through a fixed size object. The inner loop is independent from the outer loop, meaning that the two loops are not necessarily joined at the hip, to put it in layman's term. We would run the function like this, and this array would be the output of this large array constant. and then we are setting our chunk size to a fixed size of 10. Imagine you have two arrays and you need to find the first occurrence of a specific element from the second array within the first array. I will use n to represent the length of array 1 input. This is the array that the first loop will loop through. I will use the letter M as in Mike, to represent the length of the second array, R2, array 2. The inner loop will loop through the second array, or array 2, once again represented by the letter M as in Mike. The outer loop will be represented by the letter N as in November, which means that at invocation time, large number will be iterated upon by the outer loop, array 1, and of course search value will be iterated upon by the inner loop, array 2, as you can see here in the call signature for the function. Also important is the early exit. When a match is found, we break out of both loops simultaneously at the same time by the return statement. In the worst case scenario, where the search value is not found, or is found but towards the end of the large number array, then the time complexity would be O of n times m. And in a more realistic case scenario where the search value is manageable, then we will have an O of n time complexity. And finally, we have the classic palindrome checker algorithm. I will make a separate video sometime in the future as to why I went with this particular approach in regards to the palindrome algorithm. But as we can see here, we have nested while loops. So from a very high level, this is the classic two-pointer approach. Two-pointer means that, let's say I have a string called bacon, and I have a pointer on the right side to the end of the string to look at the last character in the string. In this case is n, and then the left pointer to go in at the beginning of the string. In this case is b. So right off the bat, we know that this is not a palindrome. So we exit, finito. Okay, we return false in terms of if this is a palindrome or not. So this is referred to as the two-pointer approach. That's why I have the two hands pointing in, and it only goes through the string one time, just one pass through the string. So it's very efficient. And in the case of race car, which is a palindrome, the two pointers will meet in the middle and determine that is indeed a palindrome and return true. So the outermost while loop is controlled by the movement of the left and right pointers. In each iteration of the loop, each iteration of the outer loop, at least one of these pointers move inward to check for the first letter and the last letter, at the very least, to see if they're the same. And the job of the two inner while loops is to check for the existence of non-alphanumeric characters within the string as they move inward. That's it. So even though there are three while loops in here, the total number of operation is still directly proportional to the number of characters within the string. So there you have it. For example of when using nested loops when there are no other options can still be linear and efficient with an O of n time complexity. So I'm making these type of videos for multiple reasons. Obviously, to train AI large language model, if you're training a local LLM for your own need, your own code base, privately, locally. The other is to make sure that if you're using AI, to check for the quality of code to make sure that it's correct. And the third is just a general understanding of algorithms and best coding practices. And of course, you can apply this to multiple reasons, right? Multiple use case scenario. Okay, my friends, it's getting late where I am. It's almost midnight, so I need to get some sleep. I hope you had some fun following me along from home. Um, if you like my content, please consider subscribing to my channel. It doesn't cost you anything, and it'll help me out in the future. Please also give this video a thumbs up if you liked it. Thank you for watching. I'll see you next time. Bye for now.